we will talk today about vibration of circular plate. In previous class, we talked about vibration of rectangular plate. Now we will talk about vibration of circular plate. Let me first just show you some vibrations, then we will continue. So let me share a window. Just now I opened from internet, you will see some vibrations. So it's okay. And slowly, okay, share. Okay. Can you see this? Membrane?
Yes, sir.
This membrane, so actually membrane is, this part is a membrane, right? Made from some material. Boundary is fixed. It is a circular membrane. Let me enlarge it. So now you can see it's bigger, right? So let's run it. We will see. It is waving. It's vibrating. So let's ask question, why it is vibrating like this? Why it is vibrating? If you see to this, it is initial form of membrane, right? Initial form. Then if you start experiment from this form, why this membrane should go down? Only because of tension, right? Because of tension. This initial form can be obtained by, for example, pushing with some force. So initial force. In any case, it has this form. When you run it, when you run time, then it starts moving like this. It's a very specific. What you can observe here, that vibration is it's a displacement, right? Displacement function is the same for the same radius. Means it is independent from angle. Let's say again. Okay, you can read this red line means some radius, right? Radius is some value of radius. In some value of radius, displacement is the same. So displacement depends only from radius and time also, right? It is independent from angle. You see, for any time, yeah, this red. So it means if radius is this one, then displacement of all points, the same radius is the same, whatever angle, right? So this type of vibration, we will call it radial vibrations. Radial vibrations. Let me go back. So let me admit. Someone asking admission. Where's Google Meet? Okay, admit. Let me show another wave. This wave. You can see another wave. This is different wave. You see, and this wave is different than previous one. Previous one we call it radial wave, but this is not radial because it depends not only on radius. For each radius, displacement is not the same, right? Okay. Now let's go to slide. Admit. Okay, admit. Okay. Share. Share. So unfortunately, every time I must shift my window here to admit. Admit. Okay, done. Okay. Now, today's topic is circular membrane vibration. So what we will do is our membrane has a circle shape. let's say circle again admission admit. Okay. So circle membrane. So we have seen circle membrane has a shape of circle. I will try to draw. Let's say this is a let this be circle. Oops, not the circle. Okay. Okay, let's say this is a circle. This is a membrane, has circle. What is a interesting point of circle is just okay. It has only one boundary. This is a boundary. If we place this circle in Cartesian system, let's say this is x-axis. Let be this x-axis. Let be this is y-axis. Okay. Then any point of this membrane has a components xy. So what is the boundary? How we express boundary?
Sorry, sir. Sorry to interrupt you. My friends are waiting to be admitted.
Yeah, you see, every time I have to switch my window in my computer. Okay. Tell your friend to come next time earlier. Okay, I did mention.
Okay, thank you, sir.
So boundary, how will express boundary? Boundary we can express like this: x square plus y square is equal, if this is C, let's say this point B C, equals C square. Okay? It's equals C square. This is the expression of boundary. So all points x, y, which is satisfying this equation, then this point on the boundary. Circular membrane, it's a two-dimensional thing. So we have an equation for two-dimensional wave equation. So two-dimensional 2D wave equation. What was the 2D wave equation? It is UTT is equal a square uxx plus uyy. Of course, this equation under some assumptions say no any external forces acting on this membrane, right? This equation. So A is depending from a square is equal T over rho, where T is the magnitude of the tension, and we suppose that the magnitude is a constant, and also rho is the density is also constant, right? So if you want to write boundary condition, then how you write boundary condition? We write like this: ux, y, t, when. This means when. This means when. When x squared plus y squared is equal c squared. Means xy on the boundary, right? This means when x squared plus y squared is equal c squared. Means xy point is on the boundary. Equals 0. What does it mean? Boundary fixed at the level 0. Like just we have seen. Again, someone asking to join. Okay, admit, okay. Right? So it's fixed at 0. It's fixed at 0. And of course, we needed to know information about initial conditions. So we have two initial conditions. So uxy 0 is equal fxy, right? utxy 0 is equal gxy. So fxy means initial form of the membrane, and gxy is initial speed. So this is actually a problem, and we should call this problem first boundary value problem, right? Why first? Because boundary condition has no any derivative, right? No any derivative. So no any derivative. So this is the first boundary value problem. If we try to split equation like previous case, if you try to split equation, I don't know, I have space here or not. So no, I don't have space. Let me write here. If you try to split equation, so it means if you search solution in the form of u is equal x, y, and t, as previous class, because splitting is nothing to do with boundary, right? With the shape of the plate. So you will have three equations, right? One equation for x was like this, x double prime plus lambda x equals 0. For y, we have equation y double prime plus y, mu y is equal to 0. And we have equation for t, right? So what is the problem here? Problem here is these two equations requires boundary conditions, right? We need boundary condition for this, two boundary conditions, and we need two boundary conditions for this. So this you cannot find from this boundary condition which is given here. In previous class, when we consider membranes which is a rectangle shape, a rectangle has four boundaries. That's why we have four boundary conditions. We use four boundary conditions, two for this equation for x, two for equation for y. And we solve the problem in this way. Now we cannot do this because boundary only one. So what will be solution? Solution will be we have to change system of coordinates. We did something like this for the heat conduction in circular plate. If you remember, in heat conduction circular plate, in order to solve the problem, we go to polar system. Okay. So what we will do the same thing. We will do the same thing. Okay, let me go down. So we go to polar system, x equal r cosine theta, y is equal r sine theta. So we go to polar system. Then we needed to find equation, right? UTT, our equation equal a square uxx plus uyy. That's all. We need to go to polar. T, no changes for t. My function u, x, y, t, it's actually displacement. Displacement of point x, y at time t, right? Now I change the components. Instead of writing x, y, I write it as r theta, right? The same thing, x, y or r theta, r theta. Now my function is displacement is u r theta t, not x, y, right? R theta t. Now I need to express this and this. T is the same t. You see, in both t is the same. No changes for this, but will be changes uxx, uyy. In the corresponding lecture, I don't remember the number. So when we consider heat conduction in circular plate, we find this ux, uyy. I will just remind you formulas. It was very long formulas using chain rule. We find uxx, we find uyy, right? Using just simple chain rule. When you add uxx to uyy, you will get this, right? URR, this is URR, right? Oh, not K, this is A square, must be A square, right? K in case of heat, right? URR, what about this? This is 1 over R, UR plus 1 over R square, U theta theta. This we obtain it in case of heat. It is the same. what we obtained, we just transfer this one, uxx plus uyy is equal to this, right? So that was a lecture number, I don't know, 12 maybe, just you have to check. So we did in previous classes in the same way, the same calculations, we have made this, and uxx equal uxx plus uyy is equal to this. Then you substitute, you will get this equation. This equation is the same wave equation, two-dimensional wave equation, but in polar system, right? Then in polar system, okay? In case when we have radial vibrations, what is the radial vibrations? Radial vibrations is if your function, so now your initial function fr theta, but it is, if it is independent from r, from theta, it's r, like a movie which we have seen, right? It's independent on theta. And also gr theta is independent from theta. Then motion or vibration will be radial. So radial vibration. So what will happen? Radial vibration means u will be independent from theta. Then what will happen? U theta theta's derivative will be equal 0. If u is independent from theta, first derivative with respect to theta will be 0 already, right? Then your problem will become like this. So we don't have term u theta theta. So in case of radial, so when f is a function of r, g is a function of r, then u actually will be a function of r and t, not theta. It is independent on theta, right? U r t. So it's independent from theta. So independent from theta, then it's clear that u theta is equal 0, because u is independent from theta, then its derivative with respect to theta is equal 0. And second derivative will be 0. Then you don't have this term. Then will be urr plus 1 over r ur. I'm writing here. Okay. So this will be our problem. So this vibration, we will call it radial vibrations. And you see, initial displacement also radial because it's fr. In each r, it is the same value. But if you change r, of course, fr will be changed. But it is independent from angle. So we are talking about this problem. How we will solve this problem? We will solve this problem by first splitting equation, separation of variables. So we will search solution in the form u is equal r capital is a function of r times t is a function of time. Then we will find ur. What will be ur? It will be r prime times t. You find urr, because I have in my equation urr, it is equal r double prime times t, right? So we, by separation of variables, we just switch partial derivatives into the ordinary derivatives, right? And also utt is equal r times t double prime. Then we can substitute here. If we substitute in the equation, right? Substitute into the equation. So our equation utt, which is r times t double prime, is equal a square, right? urr, which is r double prime times t, plus 1 over r. ur is r prime t, right? So this is my equation. So now let me multiply this equation to 1 over a square rt. If we multiply both sides to this, then you can see on the left side you will have t double prime over a square t, right, equal r double prime over r plus 1 over r times r prime over r. So variables are separated because what we see here, left side is a function of t, The right side is a function of radius. Radius and time are independent variables. So then these relations must be constant. You can simply fix t. If you fix time, then left side will be constant. Fix it, right? Then you try to change r, radius. Then right side is a function of r, cannot change because it is bounded by this equation. So this is constant. This constant, for convenience, let me denote by minus lambda as usual. Then we will have two equations. Left side is equal to minus lambda, and this is equal to minus lambda, right? Let me write this. T double prime over a squared t is equal to minus lambda. And another equation is we have r double prime over r plus r prime over r times r is equal to minus lambda. We have two equations, right? Two equations. So what we do is this equation we can write like this: t double prime plus lambda a squared t equals 0. This equation we know. This equation is, what is this equation? Equation 1.8 in lecture number 1. So what about this? Let me multiply this to r square r. Let me multiply this equation to r square r. If you multiply, this will be r double prime plus r prime equal minus lambda r square r, right? Lambda r square r, if you multiply. Then you can shift this lambda term to the left side. If you shift, let me use eraser. If you shift, then this will be plus equals 0. So this is the Bessel equation of 0 order. So let me remind Bessel equation for you. Oh, we have r square here, right? When we multiply, we have r square here. R square, yeah. So this is Bessel equation. Let me remind Bessel equation. Bessel equation was like this: x squared y double prime plus xy prime plus alpha square x square minus mu square r. Y is equal to 0. This is Bessel equation, right? So what we see, if we compare, that we see that nu in our equation is 0. And what we can say about lambda, lambda is alpha square, lambda is alpha square. So what will be solution of this equation? If we refer to the lecture on Bessel equation, solution of this equation will be r is equal, solution of this equation will be r is equal, J0 root of lambda, it's alpha, right? Root of lambda is alpha, actually. You can write, if you write, you can write alpha. Root of lambda, I want to write root of lambda x r, because our variable is r. This is just reminder. This is just reminder from previous class. So this is the solution. So what is a lambda? Question is, what is a lambda, right? What is a lambda? To find lambda, we will use boundary conditions. So far, we find only equation. So I cannot say anything about 1.8 so far, because if you look at lecture number 1, solution of equation 1.8 depends on the sign of this lambda a square, right? Lambda a square. A square is positive, but lambda, if lambda is 0, then it is linear function. If lambda is positive, then it is combination of sine and cosine. So we need to know what is the lambda first, right? So how we find the lambda? For this, we use boundary condition. What is the boundary condition? Our boundary condition is u, right? If you say u c t is equal to 0. Let me show you boundary condition in our problem. Okay, u c t is equal to 0. This is boundary condition, right? Boundary condition. Let me use u c t is equal to 0. What is UCT? UCT is equal RC TT, right? TT. So must be equal to 0. So what we get from this, we have option, either this t is function is 0 or this constant 0. So of course this constant must be 0 because function t cannot be 0, otherwise we have only 0 solution. So what does it mean RC0? Let me check RC. RC, it's equal J0 root of lambda, C is equal 0. So this is the equation for lambda, or for eigenvalues, right? So it is zeros of Bessel function, right? What is the Bessel function is doing? How we can find Bessel function? Bessel function graph of J0 is like this. Let me remind you. Bessel function is 0, or the start from 1, and it is oscillating, right? And damping. So each time when it is intersecting, it will give some 0. So this is 1, 0, right? This is another 0, another 0, another 0. So you see here, first 0 is positive. So from this you will find lambda 1. From this you will find lambda 2. From this you will find lambda 3, and so on. So lambda 1 less than lambda 2, less than lambda 3, etc. So we find that all lambda n are positive. So now we can find the t, because we know information about lambda. Okay. So now 818, because lambda is positive, has a solution of combination of sine and cosine. Let me say t and t is equal. What will be t and t? An times cosine a root of lambda n t plus bn sine a root of lambda n t. So you see, we can write this only when we identify lambda. When lambda is positive, we can write this. If lambda 0 can be, then this will be linear function, not combination of cosine and sine, right? So, but we see from this graph that lambda is positive. Lambda 1 is already positive, then all lambda is positive. So now I have many functions. So what my functions? My functions are un xt is equal, let me write first t, an cosine a root of lambda n t. So where lambda n is the solution of this equation, right? Solution of this equation. So plus bn sine root of lambda n forget a, but here we have a, lambda n t times j0 root of lambda n r. So this function, all of them satisfying equation, right? Because we found it from equation plus boundary conditions, right? These functions, we call them standing waves. So this is standing, we call them standing waves, okay? Standing waves. So standing waves are solution of the problem without initial conditions, right? Yeah, I have space here, I can write. So this is standing waves, okay? Standing waves. The satisfying equation and boundary conditions. So we have many standing waves, infinite number of standing waves. But our problem has also initial conditions, right? Standing wave is solution. Standing wave is satisfying un tt equal a square un un. Let me write without n. Maybe it's better to write without n. utt is equal urr plus 1 over r ur ucr is equal 0. So standing wave is satisfying this problem. Problem without initial condition. Only equation and boundary condition, right? This is standing waves. So our standing waves is above. So is above. So it's a product of Tn and the Rn. So what is the solution? Solution of problem we will search is combination of standing waves. Okay. Solution of our problem u x URT. URT, we will search in the form of combination of all standing waves, n from 1 to infinity, UNRT. So if you substitute UNRT as above, this UNRT, if you substitute this, then you will get this. This is standing waves. This is a combination of all standing waves, and we will call it traveling waves. We will call traveling waves a combination of standing waves. Now we need to find A and B coefficients. So if you use initial conditions, first initial condition U0 is equal FR. So if you say T equals 0, this cosine will be 1, sine will be 0. Then you have AN times J0, you see. From this you will find this formula for A coefficients. This is Fourier-Bessel series, right? This is Fourier-Bessel series. And you remember we have 3 cases. It is a case I. Case I was, we have this condition, J0 alpha n is the root of lambda n, right? C is equal 0. So B is C, right? C. So this is a formula. If you see this lecture on Fourier-Bessel series, you can see this formula for Fourier coefficients. Let me admit. It's too late, but people are coming again. Okay. Then in order to find B coefficients, so you see now let's note that A coefficients we find through F. So function F help us to identify A coefficients, right? So in order to find B coefficients, we use another initial condition, second initial condition. So second initial condition is this one, right? This one, second initial condition. So it means you need a derivative. We need to take derivative from this function U. Then substitute T equals 0. If you find derivative with respect to T, derivative of cosine will be sine, and sine 0 is 0. So derivative of sine is cosine, cosine 0 is 1, but from derivative you will get additional A times alpha n. Alpha n is root of lambda n, right? You just don't forget, I already written this. Root of lambda n, right? So then you will get formulas. This is also again Fourier-Bessel series. This is again case I. Then you will get this formula for B coefficients, and we notice that all B coefficients we can find through G function. So what we conclude from these two formulas which we find, so we have a solution, right? We have a solution. So then what we find, if FR 0, then what we have? We have that all A coefficients are 0. Clear? Because this is the formula. If F is 0, then A and all 0, right? If JR is 0, then what we get? All B coefficients 0. All B coefficients 0, because B coefficients we evaluate through G. Okay? Through G. So in order to evaluate this integral, I just remind you, I bring the slide. We use this formula for evaluation of integrals because we will do some exercises now. Any questions? Do you have any questions? This is some theoretical part. And I want to proceed with you with 3 exercises, not difficult. But in evaluation of coefficients, integrals involve the Bessel function. We will use this formula. As I told you in the class about Bessel functions, actually, there are many formulas for integration and differentiation of Bessel functions. This is not our goal to study in this subject, Bessel functions completely. But we can use some formulas. This is a formula for integration involved Bessel functions. Okay, so let's go to exercise number 1. So this is the pictures I will show again. I already have seen some movies about radial vibration. So radial vibration, you see, in each radius, this displacement is the same level. Radial vibration is displacement is the same level. Okay. At this another time, different time, the same membrane, but different time. You can see the same radius, displacement is the same. The same, this one, right? The same. So this different time, if you want, you can see another time. Another time, maybe the picture will be like this, right? Maybe like this, but still, for each radius, for example, this level, this line, displacement is the same. If you choose this line, then as a radius, then it is displacement level is this. If you choose this radius, then displacement is like this, and so on. So why it's happening? Because initial condition is independent from theta. Then vibration will be radial vibrations. So that's one. So let's see this example. Okay. So this is our problem. I see that A is equal 1 because no A square here. A is equal 1. C equal 1. Radius is equal 1. C equal 1. So this is boundary condition, right? This is boundary condition. U1T, right? So what does it mean, boundary condition? Boundary condition means, so we have actually membrane, radius is equal 1, and boundary is fixed at level 0, right? So no initial speed, right? This means no initial speed means G function, GR is equal 0. So we say that all Bn coefficients are 0, right? So now what about this condition? Our FR is equal 1. So why this guy is smiling? What do you think? Why this guy is smiling here? Any idea? Okay, let's just look at this problem as an engineer, not as a mathematician. Just look at this problem as an engineer. So you have what you have? You have a member, circular member, radius is 1. Boundary is fixed, where it's fixed at level 0. So what this condition says? This initial condition says initial form is at initial time when t equals 0, your membrane is lifted to the level 1, but boundary still is fixed. That's why this guy is smiling. Clear? This guy is smiling because this guy thinks it's not possible, because if you fix boundary, but at initial time, it is moved, it is shifted, all points are shifted in level 1. It looks like this. Let me just draw. Like this. Let's say this is your membrane. So it is fixed in the level 0, means this is X. Let's say this is Y. 0 means respect to Z, right? Boundary is fixed here, right? Let's say this is Z-axis, okay? Z-axis. Let B, this is 1, in Z-axis be 1. So what this condition says? This condition says, first boundary condition says, this is always, at all time, you see T, U1, T, at all time it is fixed on the ground, on the 0 level when Z equals 0. But initial condition says, at initial form was like this. This membrane was lifted here. So I will try to draw for you this. So it looks like this. let's say this is 1. So boundary is still on the ground, but inside, so means membranes itself, it is lifted. Can you imagine this? Of course, if it is perfectly flexible, it can maybe push inside of this drum like this, but boundary is fixed on the ground. So that's why it's small. But mathematically, we can write this problem about this. Then when you start the experiment, this will go down due to tension, very high tension, then this will start move. Okay. Okay, let's say, what is the solution? Oh, we don't have space to write solution. Okay, what is the solution? We have already solution, right? Only thing we need to see what will be solution. UXT, sorry, not UXT, URT, right? URT is equal, if you see formula above, so BM coefficients all 0, then solution will have this shape, sum n from 1 to infinity, an, right? Cosine A is equal 1, root of lambda n t times J0 root of lambda n r. Okay, you see, let me show you. Oh, it's okay. So if B is 0, then solution will be an cosine A is 1, right? Cosine root of lambda n t, because alpha n is root of lambda n, then J0 alpha n r, right? Alpha n, which is the root of lambda n. So solution has this shape, right? So what is the formula for an? We needed to find an and substitute here. Let me find an here. N is equal, let's go up and see formula for the coefficients, A coefficients. So A coefficients is 2 over C is 1, right? 2 over J1 square, C is 1. So it will be 2 over, when C is 1, will be 2 over J1 square alpha n, integral from 0 to 1, R this, and FR is 1, right? Okay. So 2 over J1 square alpha n, which is the root of lambda n, right? Root of lambda n, integral from 0 to 1, R J0 root of lambda n, R, then you have function is 1 dr, right? 1 dr. So we needed to evaluate this integral. This integral, for this integral, you have a formula. You go up, I give you a formula, this slide. Okay? Exactly this formula, right? Our integral was like this integral from 0 to 1, R J0 root of lambda n, R dr. So it's exactly this formula, right? Here variables x, here variables r, doesn't matter. So what is the result? Result B is 1, right? B is 1, B1. So result is, this is equal. So what will be? B is 1, J1. So alpha, which is root of lambda n, J1 root of lambda n, over root of lambda n, right? Clear? This is how we use this formula. We use this, from this we get this. J1 root of lambda n over root of lambda n. Go back to my calculations, yeah. Okay. So this integral, we know this we have this coefficient, 2J1 square root of lambda n. Then this integral, we evaluated this integral like J1 root of lambda n over root of lambda n. So then what will be? Coefficients will be 2 over root of lambda n, J1 root of lambda n, right? Root of lambda n. So then I will substitute a n here, and I can write solution here, right? solution is sum n from 1 to infinity. 2 can be written outside. So what will be this? This will be cosine root of lambda n t over root of lambda n j1 root of lambda n times j0 root of lambda n r. This is the solution. Clear? Any questions? Okay. If no questions, let's go to next exercise. Exercise number 2. Okay. Now the same, A is equal 1, and I see the C equal 1, the same equation, the same boundary condition, right? The same boundary condition. But initial condition like this, FR is 0, FR is 0. So FR is 0. So from this we can get A and coefficients are 0. But GR is 1, right? FR is 0. Let me admit. Okay. Where is my file? Okay, this file. Now, solution has a different shape. Solution has this shape, UX, sorry, not X, URT. So I've referred the formula for the solution, right? URT. Because AN is 0, now will be sum n from 1 to infinity. So what will be this? Bn sine, right? Sine A is 1, right? Root of lambda n, A is 1, root of lambda n t times J0, root of lambda n r. So this is the shape of solution. We need to evaluate and find the B coefficient, right? So what will be Bn? Bn is equal. So if we use the same formula, actually, but we have a difference for Bm. If you see Bm as in denominator, it has additional, something additional. This is right. 2, or what is the difference between A and B coefficient? B coefficient has this, A times alpha n and G. That's the difference, right? So A is 1. So if I use this formula, the same formula, but A is 1. So it will be 2 over root of lambda n, J1 square root of lambda n, right? Integral from 0 to 1, r, J0 root of lambda n, r, dr. Actually, it's the same integral. So we already evaluated this integral. It is equal. So what will be? It is equal 2 over. If you substitute the same thing, so it will be lambda n, not root of lambda n, because you see it has here root of lambda n. We have extra root of lambda n. That's the difference, because other things are the same. We have extra root of lambda n, so it will be just root of lambda n, just lambda n. G1 root of lambda n. So this is the coefficient. So F, we have root of lambda n. Here we don't have root of lambda n. Then you will substitute Bn, so solution will be URT is equal to, we can write outside, summation n from 1 to infinity. So this is sine root of lambda n t over lambda n times J1 root of lambda n times J0 root of lambda n r. So this is the solution. Clear? So let's see exercise number 3. This is our problem. Equation is the same, A equal 1 and C equal 1, right? This is the initial condition, boundary condition. The initial condition is like this. So it means, first of all, GR is equal 0. So from this we get all B coefficients 0. Right? Solution will have shape as in previous case, right? In previous case. So solution as this shape, as exercise 1, URT is equal sum n from 1 to infinity, because bn 0, only a n coefficient remain, cosine root of lambda n t times j0 root of lambda n r. Right? This shape, what was the formula for coefficients? Formula for coefficients was an is equal to over j1 square root of lambda n, right? Right? Okay, integral from 0 to 1 r times j0 root of lambda n r times this function, right? I must bring f is this function, j0 root of lambda 1, alpha 1 is root of lambda 1, root of lambda 1, r dr. So if you use orthogonality of these Bessel functions, if you remember orthogonality, this will be 0 if n is not 1, and it is equal to some number if is equal to so this will be equal, okay, I don't have this formula here. I will refer lecture on Bessel, Fourier Bessel series, lecture on Fourier Bessel series. If you see lecture on Fourier Bessel series, you will find that this will be equal to 1 if n is equal 1 and 0 if n is not 1. So then from infinite sum, you will get what? Only term 1, so it will be equal to cosine root of lambda 1 t times j0 root of lambda 1 r. So this will be solution. This is the solution. So any questions? So if no questions, that now let's just quick consider non-radial vibrations. Non-radial vibration. We have seen already movie on non-radial vibrations, right? Non-radial vibrations. So this is a problem for non-radial vibrations. So I replaced phi with theta because I needed to go for separation of variables, and so now, if vibrations are non-radial, then function depends on theta also. So I just replace theta with phi. So my function is ur phi t. Okay, I just replace theta by phi. This because capital phi is we write like this for separation of variable. Theta sometimes is same. The same. Theta is the same, right? Same. So phi capital, right? So then what will be this? This will be, what this will be? If we separate equation, so we will search solution of u. We will search u in the form of we will search u in the form of r capital function of r, phi function phi capital function of phi, function t is a function of 3. Then when you split this, split like this, I will show here for splitting. So if we say this 2 is a v, temporary, if we say this one is like vr phi, so then vr phi is r times r capital times phi capital. Then you will split into two parts like this. For T will be the same equation, 1/8, lecture number 1. Then for V, you will get this equation. Then you can split this V, because V is equal R phi. Then you will substitute here R phi. Then when you split, you will get this equation for phi. This equation for phi. So solution of this is a combination of cosine and sine. This is also lecture number 2. It is a Sturm-Liouville problem. And this equation is Bessel's equation. Bessel's equation, and you can see here nu is equal n. Nu is equal n. Nu is equal n. The solution is combination of Bessel functions. So this is the solution of phi equation. Sturm-Liouville problem, and this is a solution for Bessel equation. Bessel equation. So we split into 3 ODEs. 3 ODEs. Then your standing waves, so will be U and M. This will be standing waves. So this all functions satisfying equation plus boundary conditions. So that's why we call them standing waves. And this is a traveling wave. Traveling wave is combination of all standing waves. Then you will find the formula for coefficients. I don't go details for this. Just this is a non-radial vibration. So you see, when you have non-radial vibration, vibration will be like this, not symmetric. Non-radial vibration. So actually, this topic of non-radial vibration is not topic which we will discuss, but I just give you some introduction, some information about non-radial vibration. So you must know the radial vibrations, okay? Any questions?
No, sir.
If no questions, let me save this file. So then I will upload for you. Why it's not saving? Let's try to save. Okay, saved. Okay, I will upload this file for you. Let me stop the recording. Then recorded file also I will upload.